Hi everyone, today we are going to start 5.4, which is use medians and altitudes. A median. A median is a segment from the vertex to the midpoint of the opposite side. So this red line right here, which now I'm creating, is purple, would be a median. It starts at point C and it connects the midpoint, which in this case is point D. The centroid. The centroid is the point of concurrency of the three medians. So this is another vocab term you would need to know. So if you find the medians of each side of the triangle where they collide is called the centroid. Now, what is nice about the centroid is it's called the balancing point or the center of gravity. If you were to hold a triangle in your hand and place your finger where the centroid would be, the triangle would balance on your finger. So the concurrency of medians, once again, is called the centroid, and so here are some examples. So like I said about the balancing point, if you had a triangle and you balance the pencil, like right where the centroid is, it would balance for you. Concurrency of the medians of a triangle. The medians of a triangle intersect at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So the medians of triangle ABC meet at point P. And AP is equal to 2/3 of AE, BP is equal to 2/3 of FE, and CP is equal to 2/3 of CD. All right, so let's kind of put that together. What do you mean it's equal to 2/3 of a segment? Well, in triangle RST, Q is the centroid, so let's mark that. And SQ is equal to 8. We want to find QW and SW. Let's start with QW right here. If we know that SQ is 2/3 of the entire segment SW, well, that would mean that QW would equal 1/3 of SW, right? Because 2/3 plus 1/3 would equal an entire whole 3 out of 3. How I can figure out what QW is, an easy way is to look at this number here. All right, so I know that that is 2/3 of the entire segment, which means 1/3 would be taking that number, 8, and dividing it by 2. So if we do that, we end up getting 4. And so QW then is equal to 4. So now if I wanted to figure out what is this entire segment here, I would just add up 8 and 4 together, which would give me 12. This is going to work every time. Find the coordinates of M, the midpoint of JK. Use the median LM to find the coordinates of the centroid P. So let's look back at what a midpoint is. So a midpoint is the point in the middle, and I already drew the midpoint of JK. Remember, you just find that by looking for the coordinate that's right in between -2,7 and 6,1. So that midpoint would be 2, 4. So the red dot is our midpoint. Now, the definition of a median is a line connecting the vertex to the midpoint. So this line here is the median. The goal here is that we want to figure out where is the centroid, point P. Well, from the previous, a couple slides ago, we talked about that the centroid is located 2/3 from the vertex. So if I count the length of my median, so if I start from this point here to this red point, if I count up, I count 1, 2, 3, 4, 5, 6, 7, 8, 9. I know that my entire median is equal to 9. If I want to figure out what is 2/3 of 9, I'm going to multiply 9 by 2/3. If I plug that into my calculator, I end up getting 6. So if I start at this point L and I go down 6, I will then figure out where my centroid is located. So 1, 2, 3, 4, 5, 6 would be right here. And so that point then is point P, and it's located at 2, 1. And that is where my centroid would be located. There are 3 paths through the triangular park. Each path goes from the midpoint of one edge to the opposite corner. The paths meet at point P. Now, if you look at my diagram, I already started to mark what's congruent. If point P is my centroid and S, T, and R are midpoints, then this segment is congruent to this segment is congruent to this segment, and this segment is congruent to this segment. That's what those tick marks mean. So, number 1, if SC is equal to 2,100 feet, so let's mark that right away. SC is this length right here. So I know that this is equal to 2,100 feet. We want to find the lengths of PS and PC. Well, let's start with PC. PC is the longer segment, and we know it's 2/3 of 2,100. So plug that in your calculator. What is 2/3 of 2,100? Well, it would be 1,400. Now, if PS, the smaller segment, is 1/3 of the entire segment, I can do this 2 ways. I can do 1/3 times the 2,100, or use my trick, which is to take the longer segment and divide it by 2. So that would be 700. Let's try this again for BT. BT is this here. I'll color in red. So if BT is 1,000, let's find TC and find BC. Well, let's look at my picture. I know that BC and TC are going to be the same because point T is a midpoint. So let's just divide this by 2. And if I divide this by 2, both are going to equal 500. And lastly, PT. So if PT, which is just this small segment right here, is 800, so I'll write that right here. We want to figure out what is the length of PA, which is from here to here, as well as the entire segment TA. Well, if we go back to number 1, if I knew the long segment, I would divide it by 2 to figure out the short segment. Well, in this problem, I know the short segment, and I need to figure out PA, which is the long segment. So instead of dividing by 2, I'm going to multiply by 2. So that means that PA is going to equal 1,600. Now TA. TA is this entire segment. So to figure out what is the length of TA, I just need to add up 800 plus 1,600, which gives me 2,400. And I'm done. Next, we're going to talk about an altitude. An altitude is a perpendicular segment from the vertex to the opposite side. So this red line right here, which I'm going to now make blue, is the altitude. We start at a vertex, any vertex, and we create a 90-degree angle. Now, sometimes the altitude may be outside of the triangle. So if I go from point Q here, I can't make a 90-degree angle by going inside the triangle. The only thing I can do is stay on the outside to create that 90-degree angle. So sometimes the altitudes lie outside of the triangle. Is BD a perpendicular bisector of angle ABC? Is BD a median? Is it an altitude? So we have three vocab terms here. Perpendicular bisector. So creates a 90-degree angle as well as cuts a segment in half. Is BD a median? Well, a median is a line that goes from the vertex to the midpoint of the opposite side. And finally, an altitude is a perpendicular segment from the vertex to the opposite side. So for number 10, is it a perpendicular bisector? Well, that is yes. How do I know that? Well, point D is the midpoint because I see because of these tick marks, and it creates a 90-degree angle, perpendicular bisector. So is it a median? Yes, it is. I have a line that connects a vertex B to the midpoint D. Is it an altitude? Once again, yes. And I know that because I have a 90-degree angle. Number 11, is this a perpendicular bisector? And we're talking about this segment right here. Well, the answer is no. It is perpendicular, but it's not a bisector. These are not the same. So this is no. Is it a median? Once again, the answer is no, because D is not the midpoint. It is not in the middle of AC. So this is also no. And then finally, is it an altitude? I do see a 90-degree angle here, but remember, we have to have a segment that goes from the vertex to a side on the line that creates a 90-degree angle. So the 90-degree angle should be down here, which we see is not a 90-degree angle. So the answer here is no. Number 12, do we have a perpendicular bisector? So let's look. I do have a bisector because I see that these tick marks are the same. However, I do not see a 90-degree angle, so it's not perpendicular. So it is not a perpendicular bisector. Is BD a median? Yes. So the definition of a median is a segment that connects a vertex to the midpoint. D is the midpoint. And then is this an altitude? This would be no, because I do not see a 90-degree angle. Concurrency of the altitudes of a triangle. The lines containing the altitudes of a triangle are concurrent. The lines containing AF, BE, and CD all meet at point G. So point G, the concurrency of the altitudes, is called the orthocenter. This is something that you would want to write. Now, the orthocenter can be in different positions depending on which type of triangle you're looking at. So for acute triangles, the orthocenter is inside the triangle. Point P here would be the orthocenter. For right triangles, P is on the triangle. So P would be right here, the orthocenter. And then for obtuse triangles, the orthocenter would be outside of the triangle. So here would be our orthocenter for that example. And lastly, isosceles triangle. In an isosceles triangle, the perpendicular bisector, angle bisector, median, and altitude from the vertex angle to the base are all the same segment. In an equilateral triangle, this is true for special segments from any vertex. So isosceles triangles, as well as equilateral triangles, the orthocenter, incenter, circumcenter, and centroid would all be the same point, which is pretty cool.